Hello, and I wanted to take a moment to welcome you to AP Calculus, either AB or BC, with this warm-up exercise. And it seems really simple, right? Okay, so what you were supposed to do is write down at least 5 things you believe to be true about this graph, right? So we just have a regular good old TI-84 calculator. It's the older one, it's not a color screen, but just go with it, right? So the picture is clear enough that we could see certain things about that. And so most commonly what people say is, well, it's linear. This thing looks linear, right? And then go on from there. Okay, well, if it's linear, do we have an equation for that thing? Well, it looks like this thing has a slope, like if I come in here with my laser pointer, perhaps. Yep, there we go. It looks like I go up 1 and right 1, up 1, right. It looks like it has a slope of 1 right there, which means that its equation would be y equals 1x, or just x, and it goes through the origin, so its y-intercept is 0. So lots of these kind of things is usually what I get when people take a look at this. Maybe one more thing from your algebra days. You remember direct variation, y equals kx. In this case, your k value, your constant or proportionality seems to be 1. All right, so now what I'm going to do is flip over to an actual graph grid on a calculator. And this one is one of those nice, neat color screen ones. There you go. So zoom in. It's this nice magenta color. Ooh, look at that. That looks great, right? So usually when people ask me to do, well, let's just go ahead and hit y equals. So if I hit y equals, it doesn't show you anything because I have the actual equation hidden here. All right, so I'm going to go back to graph there. Right, and so the same thing looks to be true. It looks like it's, it's this line y equals x, a linear equation. But let me show you something. Let's look at the window setting here. I'm going to look at the window. Now, if you look at those values and think about all those things that you wrote down, all those things that you thought were true about this graph, how confident are you now? Do you think it changes anything in particular? Okay, all right, are you ready? Now, one of the things that I tend to do instead of setting window settings is I usually go to zoom, and then I choose one of the built-in zoom settings, and the one that I tend to pick a lot is zoom 4, which is zoom decimal. All right, so I'm going to just choose number 4 here. Boop. Oh man, what the heck? What in the heck? All right, let's look at the window now. All right, so look at the values on the window now and look at the graph that we have. Think about where that graph was that we saw originally and the graph that we're seeing now. What's the connection between these two things? So the graph that we were seeing before, to start off this entire lesson, here I can go back real quick. I can Alt-Tab to this thing. There we go. It looked like that straight line, but where was that straight line? Let's go back to the camera view. That straight line was just right there at the origin, and that's it. It was super, super zoomed in right there at the origin. So what do you suppose that means about this particular function right around the origin? As a matter of fact, the answer to that question is basically what this lesson is about, and it's a fantastic start to calculus in general. So coming back to the slideshow here. So our first objective, to be able to use local linearity to approximate the slope of a function at a point. That's exactly what we were just doing. Local linearity, the word local usually associated with a local minimum or a maximum. Linearity usually associated with a line. So it looks like that what we're talking about here is that locally, if I zoom in enough on a particular kind of function, it looks like a line, which is convenient because that gives me the ability to find the slope. Where's that laser pointer? Come on. No, that's not the laser point. The slope of the function at a particular point. And our second objective, second half of this, is to use an average rate of change to approximate an instantaneous rate of change. Average rate of change is the only kind of rate of change that you were able to calculate prior to calculus. It's the same thing as slope, right? The change in distance over the change in time, something like that. Or, for example, if you were taking a trip and your trip was, let's say, 120 miles and it took you 2 hours to get there, 120 divided by 2, you had an average speed or an average rate of change of 60 miles per hour, right? Instantaneous rate of change is different, and it is only calculus that allow us to calculate those things, and we do that. Like in a real-life situation, if you want the instantaneous speed of your car, all you've got to do is look down at your speedometer. But calculus gives us a way to do it, and we're going to bridge the gap between the pre-calculus idea of average rate of change and the calculus idea of an instantaneous rate of change. Your assignment here, the pages 88 and 90, that's stuff from your textbook, and then there's going to be a homework supplement that goes along with this.